Hello everyone, this is going to be another fluids video, and in this video we're going to be going over external flow, mainly covering the drag coefficient and drag force. So what I'm going to do in this video is I'm first going to go over the drag coefficient, how do we find it for different scenarios, talk about the Reynolds number and how that plays a role in it. And then after that we're going to go ahead and do this example that you see on the screen, 11-41. Okay, so to start off, I'm going to write the relation between the drag force and the drag coefficient. Okay, so we get that the force of drag is equal to the drag coefficient, CD, times the area projected, times the density, times the velocity of the flow squared, all over 2. So this is our relation here. Okay, so from here, so you might be wondering, how do we find the drag coefficient? So I'll write out a series of steps that we usually take to get the drag coefficient. So you may or may not know, but the drag coefficient, so CD, we know that depends heavily on the Reynolds number. And remember the Reynolds number, rho times velocity times diameter or length over viscosity. So what we're going to want to do, what we're going to ask ourselves here is, so for steps, what we would do is, if possible, we would find the Reynolds number. And after we find the Reynolds number, we would identify whether this is laminar, turbulent, or a combination. So in order to determine whether this is laminar, turbulent, or a combination of the two flows, we're going to have to figure out what the Reynolds number is. So typically, what we do is we call these transition Reynolds. So if this is a flow over a flat plate, for instance, so think of it, you have a plate here, and you have a flow, let's call that V. So a flow over the flat plate, so in this case the area is going to be this shaded area here. So a flow over a flat plate, as shown, if the Reynolds number is about 5 times 10 to the 5th. So if that's our Reynolds number, if it's greater than this value, then we say that it is turbulent, and if it is below that value, then we say it is laminar. So we can say that for flow over a flat plate, if the Reynolds number is less than 5 times 10 to the 5th, we say it is laminar. And of course, if it's greater than we say it's turbulent. So this value of the Reynolds number here, that only holds true for a flat plate, or a flow over a flat plate, I should say. And then our other instance or case is if we have a pipe flow, so internal flows through a pipe. So for these kinds of flows, if the Reynolds number is less than 2,300, we can say that that is laminar. And if the Reynolds number is greater than 2,300, or excuse me, 2,900 is the value, then it is turbulent. Anything within from 2,300 to 2,900 we call the transition region, and there's no true way of knowing whether it's laminar or turbulent in the transition region. You would have to go with another approach to find that. Okay, so from here, the next step would be, so after we determine whether it's laminar, turbulent, or combined flow, we would use the appropriate equations / tables / graphs to find the drag coefficient. Okay, so I'm going to zoom out a little bit here. And I'm going to continue this to the side here. Sorry about that. Okay, so to find the drag coefficient, what we would do is, obviously you already figure out if it's laminar or turbulent. So for laminar, we have, let's do it this way. So if your flow is laminar, excuse me, and let's say it's a flow over a flat plate, then we can find the drag coefficient with this following relation. So the drag coefficient is 1.328 divided by the square root of the Reynolds number okay, so that's for flow over a flat plate. And if it's turbulent, and it's also a flow over a flat plate, we have two options here. So if your Reynolds number, should do it this way, if your Reynolds number is between 5 times 10 to the 5th and between 10 to the 7th, then your drag coefficient, CDF, would equal 0.0740 divided by the Reynolds number based on length to the 1/5 power. So that's this case. And the other case is if your Reynolds number is between 10 to the 7th and 10 to the 9th. And in this scenario, then our drag coefficient can be found from this expression, 0.455 divided by log base 10 of your Reynolds number based on length, all raised to the 2.58. So remember, these are for flows over flat plates for turbulent flows. And finally, if it's combined, so if it's laminar and turbulent, or if it's laminar and then, I should say if it's laminar and then after a certain amount of a certain distance. So if you have a plate here, let's say you have a friction. You have friction on the top of the plate and the bottom. So it's rough. Let's say there's a roughness here. So this flow, let's say it comes in laminar. After a certain x distance away, so let's say here, it becomes turbulent. So after this x distance away, it is now turbulent flow. That's a very common occurrence. In that case, then we can find the drag coefficient. So I should add, this is also flow over a flat plate. And the drag coefficient is 0.455 over log base 10 of the Reynolds number length to 2.58. All of that minus 1700 divided by the Reynolds number based on length. And this is true if the Reynolds number is between 5 times 10 to the 5th, as well as 10 to the 9th. So this is just a glimpse of a couple scenarios. So obviously for these three examples that I showed you, those are all for flows over flat plates. Now there is what we call cross flow equations. So if you have a ball, I can't really draw a sphere, but if you have a cylinder, for instance, and there's flow coming in directly. So if you look at the area, this is the cross section you would see what the flow is. So in this case, there would be a different set of equations you would use because that's a different kind of flow than what we're talking about for these three. So in that case, if you look in your book, there should be a lot more relation equations you could use to find the drag coefficient. One good table I did find in the book that I'm going to write down right now is, let's use another color, is table 11-3. So this gives you drag coefficients for various shapes. And the only thing that we have to keep in mind for this is that to use table 11-3, your Reynolds number has to be greater than 10 to the 4th. So I recommend giving a look at this table. Okay, so After that, after you find your after you find your drag coefficient, really all we would have to do now is we would plug our CD into our drag force equation. So yeah, so that's pretty much the steps we would go to find the drag coefficient. So I am going to cut this video short, but I'm going to make another video covering the example that you see here. So if you want to see that video, just feel free to just click on the next one. Hope you guys enjoyed.